Hello everyone, welcome to my new video in my Mathematics Essential series. In this video I want to introduce the cosine rule and give a proof. Now the cosine rule, just like the sine rule, applies to any triangle, but if you're using the cosine rule and the sine rule to solve problems, you will be using them to solve problems to do with non-right angle triangles. Okay, otherwise you could just use the sine, the cosine, and the tangent ratios to solve problems if you're working with right angle triangles. So if you're using these rules, you're going to be working with non-right angle triangles. Okay, you can use them on right angle triangles. They hold for right angle triangles just the same. It's just that it's some unnecessary work. Okay. Now, in order to prove the cosine rule, let's first consider this triangle in the diagram where all of the angles are labeled with uppercase letters and their opposite side lengths are labeled with corresponding lowercase letters. Okay, then what the cosine rule says, okay, the cosine rule, okay, it says that if you take any side and square it, well, that's equal to the sum of the squares of the other two sides minus twice the product of the other two sides times the cosine of what angle? Well, whatever side that you squared first, okay, it's going to be the cosine of the angle that's opposite that side. So on this side, in this case, the cosine of A. Okay, now this holds for any side and opposite angle. So if you want to be taking the cosine of some other angle, then you just need to interchange the angle and the sides appropriately. Okay, so for instance, if we want to be taking the cosine of the angle B, okay, we would write the cosine rule, or it's this version of the cosine rule that we would use. B squared equals A squared plus C squared, okay, minus twice the product of A and C times the cosine of the angle opposite the side that we initially squared, so that would be the angle B. And I will write out the third way that we could write the cosine rule, just because when we do the proof, we could get any one of these three expressions, and if we prove one of them, we've proved all of them. So C squared is equal to A squared plus B squared, okay, minus twice the product of these sides, A and B, times the cosine of the angle opposite the side C. So that would be the angle capital C. Okay, so all these are equivalent, these three ways of writing the cosine rule. And in order to prove it, just consider the same triangle that I have above. Okay, but here what I've done is I've introduced this perpendicular H. Okay, and it defines two right angle triangles. It splits our triangle up into a right angle triangle on the left-hand side and a right angle triangle on the right-hand side. And I've also introduced the length of the base side of the triangle on the left. Okay, so that's X. Okay, so it follows that given that this entire length is A, okay, if we want the length of the base side of the triangle on the right-hand side, okay, which is this length here, well, the whole length is A, and we just want the part that's A without X, okay, so this length here is A minus X. Okay, now what we're going to do is we are going to apply Pythagoras' theorem to both of the right angle triangles. And you may have noticed that in these expressions for the cosine rule, okay, they look a lot like Pythagoras' theorem. Okay, if, for instance, C is the hypotenuse of a right angle triangle, then Pythagoras' theorem says that the square of the hypotenuse is equal to the sum of the squares of the other two sides. Okay, so just that expression on the right-hand side of the cosine rule without subtracting twice AB times the cosine of C would be Pythagoras' theorem. Okay, and in a way, the cosine rule is kind of Pythagoras' theorem in disguise, but Pythagoras' theorem talks about right angle triangles. The cosine rule talks about any triangle. More on that later. So let's get started with the proof, and we'll apply Pythagoras' theorem to both sides. Okay, so for the left-hand side triangle, okay, Pythagoras' theorem gives us B squared, because B is the hypotenuse of that triangle. B squared is equal to the sum of the squares of the other two sides. Well, the other two sides are X and H, so it's equal to X squared plus H squared. Okay, and if we apply Pythagoras' theorem to the triangle on the right-hand side, well, its hypotenuse is C, so we square it, and we know that that's equal to H squared plus the other side length squared. Well, the other side length is A minus X. So we have C squared equals H squared plus the whole quantity A minus X squared. Okay, now both of these expressions, or both of these equations, give us an equation for h. So the equation on the left gives us h squared equals b squared minus x squared. If we subtract x squared from both sides and we write h squared on the left, okay? And similarly, for this equation, we have h squared equals c squared minus the quantity a minus x squared, or minus the square of a minus x. Okay, now given that we have two expressions for h squared, okay, we can equate, we have two equations for h squared, okay, we can equate these two expressions. Okay, we can equate the right-hand sides, and if we do that, we have b squared minus x squared equals c squared minus the square a minus x, or the square of a minus x. Okay, now if we just resolve the square, okay, we have b squared minus x squared equals c squared minus, in brackets, a squared minus 2ax, okay, plus x squared, all in brackets with a negative sign out the front. And if we resolve that negative sign, okay, we have on the right-hand side c squared minus a squared plus 2ax minus x squared. Okay, and now you can see that on both sides of the equation, we have a negative x squared term. Okay, so those negative x squared terms will add to 0, or if you prefer, you can add x squared to both sides, and you'll be left with b squared equals c squared minus a squared plus 2ax. Okay, now if you take a look at this equation, it's starting to look a little bit like the cosine rule, but the cosine rule didn't really have x, okay, and it didn't have a negative a squared term, so somehow that has to get resolved, and the cosine of an angle doesn't appear anywhere in our equation. Nonetheless, if you take a look at the three equations we wrote down that are all just equivalent ways of expressing the cosine rule, okay, you can see that the equation that we derived looks somewhat like this one. Okay, the second one we wrote down, b squared equals a squared plus c squared minus twice ac times the cosine of the angle b. Okay, so somehow we need to sneak a term that involves the cosine of the angle b into the equation that we have derived. Now, to do this, we can just look at the triangle on the right-hand side of this diagram, and we can just take the cosine of b. So if we do this, we have the cosine of b is equal, well, cosine is adjacent over hypotenuse, and remember that this is the adjacent side to the angle b, so this would be equal to a minus x over the hypotenuse, which is c. Okay, multiplying both sides by c, we would get that c times the cosine of b equals a minus x, subtracting a from both sides, give c times the cosine of b minus a equal to negative x, and then multiplying both sides by negative 1, we have that a minus c times the cosine of b is equal to x. So now we have something we can substitute for x into the equation that we've derived. So here's x, and we're going to substitute this expression here for x, a minus c times the cosine of b. Okay, I have a short memory. Let's see if I remember it. So making that substitution gives b squared equals c squared minus a squared. Oh, don't make me scroll up. Plus 2a. Yep, I'm going back up. What was it? A minus c times the cosine of b. Okay, so that's what we're substituting in for x. A minus c times the cosine of the angle b. Okay, so now, just doing some algebraic simplification, we have b squared equals c squared minus a squared plus 2a times a. Well, that's 2a squared. All right, minus 2a times c times the cosine of b. Okay, so now you can see that we have this negative a squared term and this positive 2a squared term. So adding those will just give us a squared. So we have that b squared is equal, I'll write the a squared first, a squared plus c squared, okay, minus 2ac times the cosine of b, and that is the second equation that we wrote down for the cosine rule. Okay, so if you look at this equation that we've derived, okay, Okay, that is in fact this one here. All right. So that actually completes our proof, and we own the right to write the little square, which nowadays means the same thing as what used to be more common, QED, which is Latin for something something demonstratus, which means that which was to be shown. Okay, so that completes the proof. Now, I did make the remark earlier in the video that the cosine rule, just like the sine rule, applies to all triangles. So it must apply to right angle triangles, even though you wouldn't use the cosine rule to solve problems about right angle triangles. But you may want to see what happens if you apply the cosine rule to a right angle triangle. Try applying it to the right angle, so where you take the cosine of the right angle, and when you take the cosine of one of the non-right angles, okay, because you'll just get the same result for any of the two non-right angles in the triangle. And you'll get an expression and see if you can recognize what that expression says. Okay, if you have any questions about that or anything in this video, just post it in the comments. And if you want me to make a video of, the cosine rule and the sine rule applied to right angle triangles, I'll make one. So I think I'll leave it there. If you enjoyed this video, feel free to give it a like or a share. Like I said, questions, put them in the comments. And if you would like a notification when I upload a new video, just subscribe to my channel. Until next time, bye for now.